Amazing. So I will hand it over now to Lasha. Lasha, if you want to share your screen and.
Okay, thank you. Thank you for having me. First of all, let me share my screen. Do you see my screen?
Yeah, we can see it. Yeah.
Okay, so good evening, everyone. Once again, thank you for having me, and thank you for joining us on this book club session. So a lot of us don't know me. So my name is Lasha. I work as a data partner at a company called Tabby, and for the next hour or so, we are going to overview this amazing book, Fundamentals of Data Engineering by Joe Race and Matt Hosley. But before we begin, let me tell you what I love about this book and what we'll focus on today. So, Fundamentals of Data Engineering is structured around the data engineering lifecycle. It's not a book about a specific technology. Instead, it's about the core principles and frameworks that guide the entire data engineering lifecycle. This book is like an excellent starting point for anyone interested in this field. And well, I think it's not a light read for absolute beginners, but it can serve like a syllabus, a perfect syllabus. So you can use it to get a high-level map of the entire landscape, all its stages and components, and then use that map to, for example, guide your deep dives into specific areas or technologies. So our plan today is to follow that map. We will explore the 5 core stages of life cycle, plus the essential undercurrents like security and architecture that support them. And we'll also overview how to make smart decisions about technology and design choices. Okay, so why this book matters? As I mentioned, it's organized around the data engineering lifecycle. There are many technical books that try to teach you a single tool like Spark, Kafka, or Snowflake. And the problem is those tools evolve, change, and sometimes they get obsolete and replaced. So instead, this book takes a step back and it follows the logical flow of data from the moment of when it's created to the moment it provides business value. Once you understand this universal flow, if we trust the authors, well, I trust them and I agree with them. Once you understand this universal flow, you can rationally evaluate any technology and understand exactly where it fits in. So, second reason, it's written for a broad audience. Whether you are a software engineer moving into data or a data analyst looking to build more robust pipelines, or a manager trying to understand how your team works, this book provides a common language and framework. It somehow helps to bridge gaps between different roles. As I mentioned on the first slide, it serves as a fantastic syllabus. And how would I recommend using it is like you read it first to get the big picture map, understand the stages and the undercurrents, and then treat each chapter as a starting point for a deeper investigation into the tools, patterns, and challenges of that specific area. And finally, why I love this book is like it gives us clear distinction between data lifecycle, which covers a broad data lifecycle from data for its entire existence, and the data engineering lifecycle, which is the subset of the data lifecycle, and it is comprised of stages that data engineers directly control. So let's move on to the next slide, which is about data engineering lifecycle. The book proposes that data engineering lifecycle comprises of 5 core stages. These are generation, storage, ingestion, transformation, and serving. So generation is where data is born in various source systems. Storage, as you can see on the slide, it's a foundational layer, and it's like where data rests throughout the life cycle. Then we have ingestion. Ingestion is like a movement of data from the source system into the storage systems. In our case, storage systems are mostly analytical storage systems. Then we have transformation. Transformation is where raw data is cleaned, shaped, and refined into something useful. And to me, the most important layer is this final stage, serving layer, where the actual business value is delivered, whether through analytics, machine learning, or different applications. So it's important to know that the middle stages, storage, ingestion, transformation, and well, even serving aren't always a strict linear sequence. They can overlap, repeat, or even occur in different order. For example, you may know about ETL and ELT, where in ETL, you first transform the data and load into your warehouse. The transformation step happens during the ingestion step. And then you have ELT, where you first load the clean data into your warehouse and then apply some transformations. Yeah, in terms of serving, I mentioned it can also be in different parts of this life cycle. For example, in my experience, serving layer can be at the last stage where, for example, the golden data sets are being used by different analytics teams. But it can be also somewhere in the middle, between raw layer and golden layer. Where, for example, machine learning systems can take the data directly from the so-called silver layer. This is a middle layer between raw data sources and the golden data marts that are optimized for business intelligence and analytics. So, as you can see, below are undercurrents: security, data management, data ops, data architecture, orchestration, software engineering. It's important to note that these aren't stages you complete. They are continuous disciplines that are essential for the life cycle to function properly. And in my experience, often companies neglect them, but doing so is the number one cause of production failures. Okay, so let's move on to generation. As I mentioned before, the generation is the stage where data is created. In today's world, practically everything is generating data from your mobile applications or home appliances, like even vacuum cleaner can generate data today. And here I outline the critical steps I think is very important to know about generation and source systems. So first concept is ownership. So as a data engineers, we typically do not own the source systems, right? We are just consumers of the data sources. This means we can't change them, and we have to work with what they give us. I mean, the owners of the data sources. Therefore, a deep working understanding of these sources is very important. We need to know how data is generated, its frequency, its velocity, and its variety. So let me quickly define these frequency, velocity, and variety terms. Frequency refers to how often data is created or delivered. It is produced on a predictable schedule, like daily state reports, or is it generated continuously, like user click streams on some website. Velocity is about the speed and volume at which that data arrives. Are we talking about a few kilobytes of data per hour, or gigabytes, or even terabytes of sensor readings every minute, right? The different the velocity types require a very different architectural approaches. And then we have variety. As I mentioned, there are many types of data sources today. So modern business might need to pull data from application databases like PostgreSQL, event streams like Kafka, third-party APIs, or in many cases, just a simple CSV or Excel files, right? So each source has its own quirks and structure, and managing this diversity is a huge challenge for data engineering. Another concept when dealing with source systems is a schema. So we might have a fixed schema sources like traditional databases where we know that the specific table has a predefined structure. We know which columns these tables include and what data types they have. But we also may have the schemaless or semi-structured sources, like JSON from different APIs. These schemaless sources offer flexibility, but push the work of parsing and validation downstream to the data engineers. So we also have to plan for like schema evolution, meaning what if something changes in the data source. For example, we were waiting for 10 columns and we received 11 columns or 9 columns. Or, for example, the name of the column has changed. What do we do in these cases? So before you ingest a single byte into your data source, you might ask questions to evaluate the source systems, right? So the book provides many more questions, but I outlined here the three main questions, I would say. First of all, we need to know who owns it, what are its uptime guarantees, and how can we backfill data if there's an outage. Okay. So then we have a storage layer. Storage is the foundation of the entire data engineering lifecycle, and the choices we make here impact everything else from performance to cost. The first big decision we usually make is choosing the right storage system. This could be a data warehouse, a data lake, lakehouse, a standard database, or object storage like Amazon S3, right? So your choice depends on your access patterns and workloads. Let's briefly define these different database options. So standard database, often called a transactional or OLTP database, is designed to run the day-to-day operations of an application. It is best at processing a high volume of short, simple transactions quickly and reliably. For example, when you visit your preferred online store and make a purchase, this web application makes a simple and short inserts into the database. That's what it excels in. Then we have a data warehouse. It's a system designed specifically for business analytics. It stores large volumes of structured historical data that has already been cleaned and processed. Yeah, and the main purpose of data warehouses are to keep this history of data, to analyze the history of our business and make some informed decisions about the future. So it has a predefined schema, as I mentioned before, and it makes it highly efficient for running complex analytical queries and generating different reports. But you should have a correct data modeling um, to make the most of out of it. And then we have a data lake. It is a like centralized repository that holds vast amounts of the raw data in its native format. So in data warehouses, we have a structured data, but sometimes we need to store, for example, audio files, different, for example, images and tabular data in one storage. And that's where data lake comes in. So we can store their structured, semi-structured, or unstructured data, and structure is applied only when the data is read. So we can ingest everything we have in data lake, and when we read the data, we define its structure programmatically. So it's great for example, data science and machine learning applications. Then we have a data lakehouse. As I remember, the concept of lakehouse was first invented by Databricks, and it's a modern, I would say, hybrid system that combines the low-cost, flexible storage of a data lake with the data management and query features of a data warehouse. It aims to provide a single platform for analytics, business intelligence, and machine learning on all data types. And the final one is object storage. It's like a technology, and object storage is the foundational layer for almost every data lake out there. So the main advantage of object storage is that each object contains some metadata about the object itself. So each object contains the data itself, of course, metadata describing it, a unique ID, and yeah. So about access patterns. The key distinction is we need to make is between write-oriented and read-oriented systems. These two are very important concepts in data engineering systems. So in OLTP databases that runs a website is writes-oriented. It's designed for fast single record inserts and updates, whereas a data warehouse is read-oriented. It's designed to scan and aggregate billions of rows very quickly for analytical queries. So when you use wrong one for the job, it leads to terrible performance and high costs. Then we have a concept of temperature of data, and it is related to data access pattern. We can have hot data, warm data, and cold data. So hot data is accessed frequently and should live on the fastest and probably the most expensive storage like SSD or in-memory cache. Warm data is somewhere in the middle. It is accessed less often and can sit on a standard storage, more cheaper than the hot data. And of course, we have cold data, which is used mainly for archival and compliance purposes. So it can go on very cheap, slow storage, like AWS service Glacier. So cold data is like accessed once a year or even more rarely. Of course, performance also depends on understanding the raw ingredients of storage. For example, using compression makes data take up less space and can speed up network transfers and scans. But you should be aware that it also adds a small overhead for compressing and decompressing the data. It's also good to know about different strategies like indexing, partitioning, and clustering. So how your database system works with these concepts. And well, these are the techniques to organize data physically or logically on disk, so that our queries don't have to do a full table scan every time, which of course drastically reduces the cost and improves the speed. Let's move on ingestion patterns. This is very important. So after we identified these sources, we need to have in our data storage, whether it is a data warehouse or data lake or lakehouse, we need to ingest the data. So ingestion in simple terms is the process of moving data from its source into our storage layer. The book notes that ingestion and storage are often the most significant bottlenecks in the entire life cycle because source systems are outside of our control. I mean, outside of data engineers' control. For example, an API can change, a database can go down. I mean, the production database, or the structure of the website we are scraping can also change. So we need to be aware of these changes and have some plan how we handle these changes in our data pipelines, because these failures have a ripple effect on the everything downstream. Um, in most cases, the first decision we make when ingesting data is whether it is a batch or streaming ingestion. So in simple terms, batch ingestion runs on a predefined schedule. For example, pulling all of yesterday's sales data at midnight. It's very simple and reliable for use cases that can tolerate some delay. And streaming ingestion processes data continuously as it's created. So this is for use cases for like fraud detection when you need to analyze your data near real time. The right choice depends entirely on the business context and expectations for data timeliness. So data timeliness means like how fresh the data is. In my experience, everyone wants to have a streaming pipelines near real time information, but in most cases they don't need it. So of course, streaming is more expensive than doing just batch ingestions. So you always need to consider the actual need of the business stakeholders. So next, let me define some of the concepts of how data starts moving from source system. So we can have push, pull, and polling patterns. Push is when the source system actively sends data to us. So whenever something changes in the source system, it just sends the events to our data storage. The pull pattern is when instead of the source system sending us the events, we actively connect to the source and pull the data on our schedule. And polling is a variation of pull pattern where before we pull the data, we ask the source, "Do you have anything new for me?" And if answer is yes, then we start pulling the data. And one of the key concepts I'd like to define is this change data capture, CDC in short. It's a powerful pattern that can be either push or pull. In simple terms, it captures row-level changes from a database log in real time and allows us to stream every insert, update, and delete without putting any extra loads on the actual database objects. So as you may know, different database systems generate this write-ahead logs. It's like a full history of what happened to and what changed in any of the database objects. So in terms of outage or in terms of some kind of failure, we can reconstruct the whole database based on this database logs. Of course, these sorry, ingestion patterns, ingestion processes have its challenges, and data engineers should know how to handle different situations. For example, I mentioned the schema evolution, or this is another concept, the dead letter queue. It's like when we, for example, stream data and for example, cast different types for example, that we can have different date types in our records, and some of the and we can't cast some of the dates, but we don't want to break the entire pipeline. We somehow we take these records that failed and push it to the dead letter queue. It's a dedicated storage where we then analyze these failed records and make decisions, or for example, we can correct our pipeline and then rerun the process for the records that went to this dead letter queue. The next stage is transformation and modeling. So transformation is where we change data from its original raw form into something useful for downstream consumers. This is where a huge amount of a data engineer's work happens, and it's primarily driven by business logic. So we can separate three stages in transformation in our pipelines. First, we have a basic transformations that might include casting data into the correct types, removing bad records, and standardizing different formats. Then we perform more complex work. This is where, for example, data modeling comes in. We might normalize the data, or we might use star schema for analytics. We might create one big table for machine learning applications. And finally, we might perform large-scale aggregations. Aggregations are also some kind of transformations to pre-compute metrics for different reports, or for example, featureize data to create predictive signals for a machine learning model. And we also have different update patterns when dealing with transformations. These are truncate and reload. This is very inefficient because, as the name suggests, we wipe the entire table first and reload it again. And often it relates to full scans of the full history of our tables, data sources. And yeah, it's very inefficient, but unfortunately, it's very common in many companies. Then we have insert only or append only pattern. This is, for example, in my current company, when we ingest data from different data sources into our first layer called bronze layer, we have this insert only or append only tables. So, for example, if something changes in database, production database, we don't change it or update our bronze layer. We only append the new record, so that we always know what and when changed in different data objects. And the last one is upsert and merge. I would say this is most common pattern, where we decide intelligently to insert new rows or update existing rows based on some kind of primary key. Of course, during transformation, there are many optimization and optimization techniques. For example, one way we can optimize our pipelines is to use materialized views, which are essentially stored query results that are periodically refreshed. And this saves the database from having to recompute a complex join or aggregation every single time, for example, someone views a dashboard. So the last layer in our data engineering lifecycle is a serving layer, as I mentioned before on my first or second slide. I think it's the most important layer of all. It's where we finally get value from all our hard work, right? So as the book says, data projects must be intentional. So we have to constantly ask what is the business purpose of the data we are collecting and cleaning. Because I've seen many pipelines that collect data from many different sources, but then there is no one who uses this data. Of course, every data pipeline is connected to cost, and we don't need data that will become obsolete or we will never use it. So the main use cases for the serving layer might be analytics, machine learning, and reverse ETL. So in analytics, we can have operational analytics. This is like real-time monitoring of business processes. We can have business intelligence that is related to dashboards for different business use cases. And also we can have customer-facing analytics. This customer-facing analytics is related to embedded reports, which are like embedded or included in the application itself, which customer can access, and our customer can see the reports about their spending, for example, their transactions or anything else. And of course, we have the machine learning use case. Data engineers frequently work with machine learning engineers and data scientists. They provide trustworthy and curated data to ML models for training and inference. So what a data engineer needs to know here is how to provide clean and point-in-time correct data to avoid common machine learning pitfalls. Of course, we don't want to train our machine learning models on incorrect or outdated data, right? And the last use case is reverse ETL. This is a powerful pattern, I would say. Instead of just analyzing data in warehouse, we push curated insights back into the operational tools or the databases. So, for example, we might ingest data from different systems about customers, analyze it, enrich the customer details, and then push this whole entire information about our customers into the tools like Salesforce, for example. And yeah, well, we can use it to drive more business decisions. So one of the concepts I wanted to tell you about is this logic on read. This is a common approach in modern analytics, and this means we load clean data into the warehouse first, and the complex business logic and aggregations are applied at query time. It resembles an ELT approach. So this is very trendy right now, and it like provides maximum flexibility for ad hoc analysis and self-service. This self-service reporting is very trendy in today's data engineering landscape. So we discussed the core stages of data engineering lifecycle, but we also need to discuss these 6 undercurrents. So the lifecycle stages are like what we do, but the undercurrents are how we do it successfully and professionally. And as I mentioned before, these are continuous disciplines. These are not like we do it one time and it works throughout the life cycle. About security. Of course, this is a very important concept in data engineering. We often follow the so-called principle of least privilege, which has 2 parts to it. It's like we give a user access to only the essential data they need, and only for the duration of time they need. Also, we should consider security in transit and at rest. So, for example, when we ingest data from source systems into our data storage, of course, the data travels through the network, and it means the data is in transit. So we should be able to protect data in transit. And when we ingest data into our storage layer, when we store data there, it means it's at rest. So we might apply different encryption approaches or masking, for example, to protect data from um, yeah to protect it. So next we have data management. This is a very broad category, I would say, that includes data governance, who owns the data, data quality, can I trust this data, and metadata management. So metadata is data about data. Data governance also covers an ethical responsibility to handle data correctly, especially so-called PII data. It's personally identifiable information, and data management is very important to be compliant with the different regulations like GDPR or CCPA. So then we have data ops. Data ops is all about automation, monitoring, CI/CD pipelines. So, for example, we use version control for our code. We have automated tests, and we have different monitoring and incident response procedures. So, for example, when you push some changes to the GitLab repository, the automated tests are run, and before you merge your branch to the main branch, you already know beforehand if something will fail, and you have the ability to fix it and then merge it to the main branch. Then we have data architecture, but let me speak about it in my next slide. We have also undercurrent called orchestration. This is like coordination of all our data jobs. A common misconception here is that an orchestrator like Airflow or Duckster, for example, is just a scheduler like cron. It's not. Cron is only aware of time, so you can only schedule your job in on specific times. But an orchestration engine is aware of different dependencies. It uses directed acyclic graphs, DAG in short, for example, to ensure that task C only runs after both task A and task B have successfully completed. It also handles retries, alerting, and different backfill procedures. So orchestration is much more than just cron jobs. And we also have software engineering undercurrent. It's because as a data engineers, we try to employ different software engineering best practices to our work. Um, and yeah, because for example, we use same tooling like Git and others. For example, many data engineering projects are built in Docker containers, and yeah, it's very similar nowadays to software engineering practices. So, how do we define a good enough data architecture? First of all, I would say data architecture is the design of systems to support the evolving data needs of an enterprise, of a company, right? So the book gives a great piece of advice. Never shoot for the best architecture, but rather the least worst architecture. So you should make flexible, reversible decisions by carefully evaluating trade-offs. Some key principles for data architecture are building loosely coupled systems. This is the idea behind microservices and event-driven architectures. By having independent components, a failure of one system does not cascade and take down the entire system. So we need to be building decoupled systems. Um, another um, Another principle is like plan for failure, because as the famous saying goes, everything fails all the time. So you need to be aware of your recovery time objective, so-called RTO. It means how quickly must you recover after a failure, and your recovery point objective, RPO. This is how much data can you afford to lose. So if you plan for failure and um, you make your data redundant and you use different replication approaches, it's yeah, it's best to go with that approach. And then we have architect for scalability. This means that our data systems should be elastic. What do I mean by elastic? Um, when, for example, there is more load than, um, I mean, our systems should be able to scale up to handle load, but also scale down to save money, of course. And truly elastic system can even scale to zero. So it means we can shut down completely our system when it's not in use. And the last principle is embrace FinOps. Of course, everything we do is related to cost. So cost is an architectural constraint, and we must be able to track and attribute different data pipeline costs to specific projects or teams. So, how do we select correct technology for our projects? Here are several key considerations from the book. We have team size and capabilities. So, for example, a small team with limited operation bandwidth will benefit from managed services. Managed services are, for example, services from AWS or Google Cloud. We have speed to market. Sometimes the opportunity cost of building something yourself is too high. So buying or renting a solution can get you to market faster. We have to make choice between build versus buy. It is also related to speed to market, of course. So, for example, um, if we want to build something that will give our business competitive advantage, then we should go for it and build ourselves. But we can buy things, for example, to related to logging or orchestration. These systems are very common among different companies, and we don't have to waste our time and capabilities to build the new solution, to invent the wheel by ourselves. Of course, the location is one of the key considerations when selecting a technology, um, especially when we need to choose between different cloud providers. So we might need to ask questions like, do regulations require your data to be on premise, or you can upload the data in cloud. Um, also, uh, there also exist different hybrid or multi-cloud approaches, which gives you some flexibility, but of course it adds significant complexity. And another choice we can make is between serverless versus servers. So serverless options offload huge amounts of infrastructure management, but can lead to vendor lock-in. It means if you choose, for example, AWS, you have to use AWS um, services or AWS compliant services. But running your own clusters gives you more control, Of course, it requires more operational overhead. Um, Ultimately, the best technologies are the ones that integrate seamlessly with your undercurrents. It should integrate with your security model, with your CI/CD pipelines, and different monitoring stacks. And I would say it's more important to have interoperable tools and choose the tool that works with your current tools perfectly than just choose the tool based on the benchmarks. Because these benchmarks are done mostly in isolated environments and does not take into account different integrations with different tools. So, what the future of data engineering looks like? Um, the book highlights several key trends that are already reshaping our work. Um, Real-time by default, the expectation is shifting from next-day reports to instant feedback. But as I mentioned before, it's very important to consider the exact business need because everyone wants real-time data, but not everyone needs it. Data contracts and automated lineage is very trendy in today's data engineering landscape. So it's important to combat poor data quality. The industry is moving toward enforceable version control schemas at the source. Um, and we have, of course, AI-assisted engineering. Large language models, for example, are already helping us write different code, whether it is Python, Java, or SQL. In my practice, it's more common to write code in Python using LLMs than in SQL because I think when you write SQL code, you need to have more context about your underlying data. And if you don't give it to the large language model, it might output the perfectly working code, but it will output the incorrect results because LLM does not know the underlying logic behind the data tables we have. But yeah, the engineer's role will shift more towards validation, governance, and applying deep domain expertise because different AI solutions propose um, AI solutions help us optimize, for example, costs, flag different security risks. And this is why many of the data engineering tasks are automated, and we need to shift toward domain expertise. And the last one is role convergence. It's like the traditional gap between software engineering, data engineering, and analytics engineering are breaking down, and teams are using shared toolkit, as I mentioned before. For example, Git, containers, different CI/CD pipelines, and higher level abstractions are making it easier for people to work across the full data lifecycle. And this is my last slide about three key takeaways from this book. So the first one is think about life cycles, not specific technologies. The second one is undercurrents decide production success. And of course, architecture is continuous process and it's all about trade-offs. So your goal is not a perfect final design, but a flexible, reversible one that can evolve. So we should plan for failure, measure our costs and performance, and always be iterating. Thank you. I hope you liked the presentation. Now you can ask any questions about my presentation or any topic from the book.
Thank you. Thank you, Lasha.
Yeah, thank you so much for doing this. Yeah, it was really, really good. I think yeah, I kind of asked a few volunteers maybe to come up with some questions. It's okay if you don't, but if anyone does have any questions now, now would be the time to ask. And just while everyone's thinking of their questions, I'm going to quickly post in the chat as well, just a form for kind of a survey on if you like the format of the book club, or if you have any other suggestions, or kind of suggestions for other books as well, although you can obviously also put that in the Slack channel. And yeah, if anyone is having trouble joining the Slack channel, do let me know. Would be great to have lots of people voting on the next book. So yeah, let me know if you have any trouble with that. And otherwise, yeah, I'll leave it open to questions.
So I have a question, which I always confuse. The book separates data engineering from data science, but since both work with data, and is that distinction really meaningful? I mean, because in some companies, data engineers also build some models. So where does one role end and the other role begin? What do you think?
Yeah, that's a good question. So I agree with you. In some companies, many data scientists also build different data engineering pipelines.
Yeah.
And many data engineers also build models. But I would say data engineering and data science are very broad subjects on its own. So, for example, data engineering has many best practices, many patterns that you can apply to different kinds of ingestion processes, different kinds of data pipelines that data scientists might not know about. And on the other hand, data engineers are not required, usually are not required to know about different machine learning models, right? Because machine learning and data science is all about predicting the future. Of course, they use data and they use data from data lakes, data warehouses. But data scientists most often, well, in my experience, are not aware of best practices of how to build those data models in data warehouses and data lakes. And data engineers are the people who should know this, who should know how to treat different types of data, how different formats of data, for example, audio, tabular, and image data. And for example, different data science directions. For example, I don't know, image processing.
Yeah.
We have I mean, data scientists use different types of data, right? We might use tabular data. We might use images to predict some kind of future. But to optimize the processes that generate those data, it's a job of data engineers and not data scientists.
Yeah.
And of course, there is a blurry distinction between data analysts and data engineers in many companies.
Yeah.
It's the same situation as with data scientists, right? But many of the problems arise when you when you make data analysts responsible for data engineering pipelines. Yes, many of the data analysts and data scientists can query the data in efficient manner, but in my experience, they are more oriented on the results, the output, than the best practices of how this data is generated and how we should query this data in most performant manners.
Yeah. Okay. Thank you. Thank you so much.
Thank you.
Yeah, I would say at my last company as well, there's quite a big distinction between kind of the data science team and data engineering team, because data science team, a lot of it is like experimental. So working in notebooks, a lot of it is almost like not throwaway code, but, it is a lot of kind of just experimental. Like it doesn't, looking for the absolute best architecture. So I think, whereas I think we didn't know a whole lot about, how does it how does it happen with the warehouse? We just didn't really care. It was like, just give us the data.
Yeah, exactly. And data engineers also think about the data systems itself. So whether we should use Airflow for orchestration, whether we should use HDFS for our storage or something like that. But data scientists just query the data, use the data, and I would say data scientists are one of the consumers of data engineering teams.
Yeah, okay, thank you.
Yeah, and so the consumer, I found it really interesting in the book how it's saying kind of data engineers are almost consumers of like the source system, almost kind of downstream of the software engineers. I hadn't really thought about it in that sense. Thought that was interesting. Yeah, sorry, I will move the floor open as well if anyone else has any questions. Or I can just ask as well, because obviously, Lasha, you've got some experience. I'm just wondering from your personal experience if you have any kind of top tips, or like, if from a data science side, or maybe like people who are in leadership positions as well, like what do people not know about data engineering that it would be helpful for more people to know?
Yeah, I would say many people think data engineering is easy. Yeah, as a data engineer, we make a lot of decisions about how we should model data, how we should transfer data from different source systems, from different. I would say sometimes you don't use source systems, but for example, in microservice architecture, you give ability to different teams to have their, for example, database, have their system, have them build their own systems. But when it comes to transferring data from one system to another, it's very complicated sometimes, because different systems use different formats of data. And then we also have different volumes of data, and we need to be aware of many best practices and many data patterns throughout this data engineering life cycles. Yeah, we have to make many decisions to store and to transfer data as quickly as possible.
Yeah, I think I was a little intimidated going through the book. It said fundamentals. It was like, oh, there's some very complicated topics on here. And the book was kind of like, okay,
it's not fundamentals. It's
all of everything about like querying data, and everything about software engineering, and everything about coding. It's like, okay, this is not an easy job. Yeah. But yeah, so I guess maybe just like have people a bit more aware of like there are a lot of decisions that are being made, and yeah, I like it. Anyone else? You can post in the chat as well if you prefer.
I'll ask just one question about data letter queues. You mentioned this name, like when, for example, data is not ingested successfully, and like, for example, is it like in all companies that if data is not ingested successfully, then it's stored in this separate location, which called this data letter queue, or it's like up to the company to choose what method will they choose in that case?
Well, it's like a common term, general term but we can use different systems or different approaches for this data letter queue. But in general, you're right. So it's used to store failed data in separated storage, and then we can analyze the failures, what have failed, and potentially improve our pipelines to sorry. Yeah, improve our pipelines to, for example, if we receive the same kind of data in the future, our pipeline does not fail.
Okay. For example, I don't know, I was listening to data engineers, and for example, if data was duplicated or something was not ingested correctly,
Mhm.
they would rerun the process from the beginning. Like they would not store this wrong data separately or something like that.
I would say it's not about duplication, and generally it's not a good practice to just hit the button and rerun the whole process. We should always try to investigate why the duplicate records were received. But the letter queue is about, for example, in my personal experience, we had a pipeline where we received data from different Excel files. And as you know, Excel files are filled mostly manually. And for example, we have a date field, and we should cast the date field into our format, general format. And some of the records were failed because the date was filled in incorrect with incorrect format. So these records will go through this data letter queue. We will store it separately, and then we investigate the issue, identify that this is because the date was in incorrect format, and then make some decisions for future use cases.
Oh, that's interesting. I have not heard about that before.
Yeah, it's new to me as well. It was interesting reading the book. Yeah.
I mean, I couldn't read the book because, I mean, it was too different from the thing I'm interested in. Even though I'm in data science, I mean, it was really kind of curious that I couldn't read the book because I didn't like it. I mean, I couldn't read it.
Yeah, it's very vast subject, data engineering, and especially if you add these undercurrents, it becomes so huge.
Yeah, but thanks for the explanation. The example was great because I haven't met something like that before.
Thank you for the question.
Yeah, I have another question, just related to like security. I just want to understand, like from your experience, have you come across any security leaks and how were they handled in real time? Like after a leak was discovered, and how were the systems changed or the existing data modified to make sure that the leak is fixed?
Yeah, to be honest, I haven't come across that kind of leaks in my
He's a good
experience.
architect for
Yeah.
this.
Yeah, because he read the book, so yeah.
Yeah, mainly it's about like personally identifiable information. For example, um, I've seen companies where everyone has access to everything, and it's not a good approach. So, for example, different data analysts can have access to, for example, customer information, but they should not have access to my personal information. For example, like personal IDs or SSNs or something like that. So it's we usually mask data like that. Masking is like when you take the value of the column from the column and you somehow change it. For example, you might add asterisks in between, or you might generate random value based on the initial value. For example, card number is a very good example where in all companies I've worked with, the card number is always with asterisks in the middle. We only know the first six and the last four digits because it has business meaning. The middle numbers does not have business meaning, and that's why they are masked.
Right.
Is that like a bank card?
Yes.
So
the
you
first
see that information at all?
sorry?
Like, can somebody access that data then, or like how is it?
Yeah,
You
I don't know how someone can use my card number only without additional information, but well, it's personal information, so not everyone should have access to it.
Mhm. Right. Yeah. Anyone else, as I said, feel free to post in the chat as well. If not, I'll say a big thank you again to Lasha. I know it's quite late for you in Georgia. Yeah. So no, really, really appreciate you doing this. It was great as well to just kind of have, be able to share your experience. So really appreciate it. And yeah, hope to see you all for the next book club, which we don't have a date yet, but I think we're getting pretty close to choosing the book in the poll. So yeah, stay up to date on the book club channel and hope to see lots of you again.
Thank you.
Thanks, Silke. Thanks, Lasha.
Bye.
Yeah, bye.
Thank you.
Thank you.